transformer. So the goal will be that we can input a sequence of tokens, and for each token we get a probability distribution for predicting the next token, the following token. So often we think that a transformer or language model is something that predicts the next token. So we give it a sequence and it gives us the next one. But when we think of transformers here, we will think about we have a whole sequence, and for each of them we have a prediction of what is coming after. And this is also why it can be trained, because we know what is actually coming after, except for the last one. We do not know because the sequence ended there. So we have a sequence. Hi there, how are. So the first thing we will need is a vocabulary, X. And we can think of it as a dictionary where it says 0, 1, 2, 3, all the way until some number of different tokens that exist in our vocabulary. And for each of these we have then a word. So hi, love, there, car, how, are, etc. So for all of these until some weird word, it's a Danish word for eel, and also here we have bus. So no, we will have you. So the first step, which is very easy to program, you could imagine, is something that encodes a string, or no, a sequence of words. We will skip the idea of how you get these words as specific things. So hi there, how are you? So we will not think about commas, we'll just think that this is some kind of sequence, and we can think of it as a vector in some kind of space with some length t. And for simplicity we might assume, no, let's just skip the details of that. So how are we doing this? We say hi, it's number 1, there is 3, how is 5, are is 6, 1, 3, 5, 6. Great. Then the first thing we need to do is we're gonna associate with each word with a vector. So we will have an embedding matrix E in, and it has a certain shape. It has d times number of distinct words in this dictionary here. So in a way we can think, if we want, that actually besides just having the ID of the word and the actual word, and we also have the embedding vector. So you don't even have to think about why it's called embedding, it's just some word. It's just that we have a vector for each of them. So this might be 0.5 2.7 and 9.3, and this one has some other thing, and all has 3, 9.2 minus 4, 11. Great, and these are the vectors, and it's very easy now because we just look vector where 1, it had this up here. I should have some way of showing you where I'm pointing. What is this? Oh. So hi, we are here, hi, we go over here and say this is where we are, and for each of these words we now get some vector, and this will be the embedding. So we have hi there, how are you? I'll just check if I'm actually streaming. It seems I am. Okay. Oh, now something is broken. I cannot do anything. Weird. Okay. So this thing that we have now is called the residual stream. What do I mean by the residual stream? I mean that we have a vector for each word. And how we're going to do it now is we're going to go through a bunch of layers. Layers S from 1 to S. And at each point we will have some kind of residual stream. We'll have some vector R. Oh. We will have some vectors that are, I will call R, and I will associate it with a specific depth 0, and then I will associate it with a specific time. I will look at this as sequence, hi there, how are you, and this will be 0, 1, 2, 3 in time. And therefore I will here have 0, then I will have another vector R, it will have the same depth, but it will have another time. And again, I hope you get the idea that these are all the vectors that we started out with. We found them in the vocabulary lookup matrix EIN, and we just inserted them next to each other in a matrix. So this is where we are now, and we could call this, if we wanted to, we could say they are all in, they're all vectors. So if we want a bit of math, we can write it as RD, where D is this dimensionality of residual stream vectors. But in practice, we might have a matrix here. So we might have some matrix X, or R, I could call it R. Might it be, can I use a big R? I could. R0. R0 is a matrix, and in practice, just to foreshadow it a bit, we could have many sequences at once, and they would all have the same length. If they did not have the same length, we would just add some space token, some word that says, there's nothing here, there's nothing here, there's nothing here. So in practice, this vector, this matrix, might be a matrix that has a certain number of sequences. We will use B, the word B for this. So B is batch size, meaning number of sequences at once. So I will not just only send one sequence through, I will send multiple, but this is not something you have to think about. Just think of it as a single sequence. And then I will have some kind of, so this we'll just have it in a parenthesis. This is not something we'll think so much about, maybe actually forget it. And then we will have t vectors, and then each will have a dimension d. Great. So this is pretty easy to program, right? Like you have the matrix, you make it very big, you fill it with random numbers in, or you, if it's a transformer that is not very good at predicting when you start out before training, or somebody tells you what the matrix is, and you just look up for each of the words, what exactly is the vector I put at each point in the residual stream. Now we then go to S0, layer 0. And what will happen here is that this layer will tell us what we need to add onto each vector in order to get to the next layer of the residual stream. So the layer is now 1. The depth is now 1. I will call this depth. And this I will call time. So now we get to this point. It's 1. And for all the vectors we have these things. And we do this a ton of times. In some things we could have probably 50, I don't know if maybe there are some with 100, but it also depends on different use cases. I believe there's some stuff showing that maybe you need more layers if you have some reasoning, or in some cases you do something else. So this is the idea. And then at the very end, so we continue down and we get, so I just, to make sure you're with me here, we get 1 here, and then we get the last layer, layer S, or S minus 1 I guess, because we have 0 to S minus 1. And then we get these, and they are called R S minus 1 of T. For some, all these are different times T, and they still live in the same size space RD, because D is the dimensionality of this residual stream vectors. Okay, and we told ourselves that for each token we get a probability distribution for predicting the next token. So this means that I want to, for each token, I want to predict the next token. Hi, there, how are you? And how does this work? Well, we have to think again. I'll just write it here. We need to get this vector into a probability distribution for the next token. How do I do this? Well, I create a matrix that's called E out. And it is a matrix, and it has as many rows as there are words in the dictionary, and it has exactly D columns, which is very nice because it is possible now to say E out, multiply that on the vector for high. So it's a vector. I will call it R S minus 1. That is the last vector for a specific time t. So this could, for example, be the there. And what do I get out? I would get out something that would maybe be called set I. Set T. Set T. And how big is this vector? Well, I multiply it by a lot of rows. So this is in Rx. That's pretty good, because what does it mean to have a probability distribution over the next token? When I have to guess the next token, I want that all the words hi, love, all, how, bus. I want to have some kind of hi there, love. That makes a lot of sense. Hi there, hi, nah. Hi there, all. Okay, okay. Hi there, bus, nah. Hi there, how. Ooh, that's pretty good. 0.3, 0.001, etc. We want a vector with that many words. 0.01, 0.3, 0.001. So how can we get that? Well, this is a vector. We multiply it, we get a bigger vector. We use the softmax. Softmax just says I have this vector set of t, and I now want to turn it into a probability distribution, so I just have to make sure they're positive and sum to 1. Goal. So these should not be negative, non-negative. And the way I do it is I will call it Q, I think. Q I. So now it's getting a bit interesting. I of t is going to be the exponentiated version of the entry that I have. So set t and the ith entry. So what do I mean by the ith entry? Well, this is a vector. It has some numbers that say this is the q. Qt is a vector, and set t is not summing to 1. That's bad. So I have maybe -3 here. I have 2. I have -4. and love was 0.1, so maybe it's 1.2, etc. I'm just exponentiating them and making sure that they sum to 1, so I also divide by the total thing that I get after. So all the things that I exponentiated. Oh, I'm aware that I should be a bit more up here. J of t. So this might look confusing, but it is just somehow looking more confusing than it is. Just take all these vectors that you got after multiplying this matrix on, and exponentiate everything, and divide by the sum for every entry. Then it sums to 1, right? And it's all positive. Perfect. So this is qt. This is the vector, and each entry in it I will write qi. So if I want to predict hi there, how are you, what will I do? I will take the softmax of the product of e out multiplied onto the residual stream vector r, add layer, the last layer, si-1, at position 0, 1, 2, how are you, 2. Softmax here, I just mean the vector. This is a whole vector. It lives in R, so it's a probability distribution, and I call this Q of 2. And most importantly, I'm interested in looking at hi there, how are you? So let's go back up and look at what number R had. Hi there, how are you? That had number 6. Number 6. So R is in a way number 6. This is 6. Then that means if this is a vector, I might be interested in this element, Q2, because that is for how. And then I'm interested in entry number 6, because that would be hi there, how. And now I'm messing a bit around, but it would be some distribution, and it would say that is actually 0.2, and I would say okay, it actually occurred like that. So it was occurring. So how surprised were you? Well, Alice is saying hi there, how are you? And Bob was trying to guess with his language model what happened after how, and he said that he believed that was 20% chance that it would be R. So how surprised was he? Well, if we use the definition of surprise, he was minus Q of R given hi, how are, no, hi there, yeah, hi there, how are, and that was his model of text, and it was minus log Q of minus log 0.2. That is how surprised he is. Good. So now we kind of have the idea that what does it mean to predict. We have not yet talked about how we actually build these layers, and this is of course advanced, and we will more advanced than just understanding the outer thing, but this is a good foundation for understanding it. So let's just recap it. Transformer. We have an input sequence of tokens, and for each token we want to predict the next token, that means we want a probability distribution on the set of tokens that tells you how much you believe each token will be the next token. So if you have hi there, how are, what you want for each token is hi there, how, predict whether it's going to be r that is next, and so on. And how do we do this? We first make a vocabulary where we give a number to each word in the dictionary. And so we think that someone is giving us these sequence of words, and they decided what counts as a token. And we list them so that we can work with numbers instead. And we say hi there, how are, it is hi is 1, there is 3, how is 5, r is 6. Great. Then for each different token in the vocabulary, we have a vector. It has some size, and we think that it is d. And the way in practice we do it is that we then look it up. What is the row 1? Okay, it was this vector. Okay, number 3 was another vector, and so on. And then we are taking these vectors that we found, and we're putting them next to each other. We're putting them next to each other like this. And they are called now the residual stream. And we think that there's a time dimension where the sequence dimension is 0, 1, 2, 3. So how is always corresponding to time 2. And then we think that there are different depths of this residual stream where the vectors are being updated by different layers, transformer blocks at different depths, 0 to s minus 1. And therefore, when we are done with all this processing, we are down here, and for each of the hi there, how are you, we have a residual stream vector that's called r, and then the t is the specific position in the sequence, and s minus 1 is the big S, is the last layer. And these vectors live in Rd, which is the residual stream dimension, but we want for each token to be able to predict the next token. So we want a probability distribution out of this vector that allows us to talk about the probability that, for example, it would be how that is coming around. What we do is we take the associated vector and we multiply it by a huge matrix that would be telling us a value for each word in the dictionary. And we apply the softmax function to make sure that it's sums to 1 and are strictly positive or non-negative. And we have now a vector that is equivalent to a probability distribution. And we can look at how surprised we get when we then observe the next word. If the next word might be word number 6, then we look at the 6th entry in our associated probability distribution, and we take the minus log of that, and this is our surprise. Great. So how does now a single thing work? How does it work here?